Hi, I'm Ben-Yaakov. This presentation is entitled Right Half Plane Zero in Power Electronics, Origin, Implications, Misconceptions, and Solutions. Let me start off with the formal definition of a minimum and non-minimum phase system. Here's the definition from Wikipedia. Now, a linear time-invariant system is said to be minimum phase if the system and the inverse are casual and stable. We are interested in non-minimum phase, a non-minimum phase system or transfer function will have zero in the right half plane, that is the right side of the complex plane, a consequence of zeros in the right half plane is that the inverted function is non-stable. That is, if we have a transfer function, we have a right half plane 0. This is the minus here, meaning that we are going to have the 0 here. Then when we invert it, here it is, then we are going to have a pole in the right side of the complex plane, and this is obviously an unstable system. So this is the test, and therefore having a 0 at the right half plane side, then this would mean that the system is a non-minimum phase. Let's see first of all what is the behavior of such a 0. Now here is the frequency domain, 1 minus j omega over omega z. This is the location of the 0, and as far as the magnitude goes, it'll be exactly the same like the regular 0 because it's going up. As the frequency goes up, it's going up in 20 dB per decade. However, the phase is now lagging. This is in contrast to the normal left half plane 0, in which we have a lead of 90 degrees. So that's the main difference. Magnitude is the same, phase is much different. In the time domain, a regular 0, this is a regular 0, is actually a derivative. This is the operator of derivation. And therefore, if you have an input like this with a constant slope, you're going to have a constant value during this time, and the value here is the slope of this input. In the case of the right half plane 0, the same thing. It's again a derivative, but there is a minus sign here. So for this, you're going to get a minus pulse like this. So this will be the difference between these two in the time domain. So let's have a look, first of all, at the question, why is this called minimum phase? Now, I've looked up the internet. I didn't find a good explanation. So here is my intuitive explanation without too many equations involved. So let's first of all look at the poles and 0, the regular poles and 0. It's the left side, nothing special about them. In a pole we have a minus 20 dB per decade drop. We have a maximum of a 90 degree phase lag. In the case of a 0, we have a plus 20 dB per decade rise, and then we have a lead of plus 90 degrees. So let's have a look now at the system, the transfer function, that has poles and zeros, and here is just an exercise. I have a pole here, I have minus 20 dB drop, minus 90 degrees phase lag, another pole, another 90 degree lag, another drop, so it's minus 40 dB per decade. Now I have a 0, so it's going up, plus 90 degree, and the slope now is again minus 20. I have another 0, it comes back to 0, the slope, and the phase goes to 0 also. And then I have another pole, dropping the phase to minus 90 degrees, and the slope will be minus 20 dB per decade. It is important to realize that once I reach the minus 20 dB per decade drop, the phase shift is fixed for the system. That is, all these phase shifts of the poles and 0 are actually canceling each other until I got to this point, and I left with one pole and one phase shift related to this pole. no matter what's in this history here. If it would have been in minus 40 dB per decade, I could have said that the maximum phase shift would be minus 180. Now, if this zero would be a right half plane zero here, the slopes are the same because the slope of the right half plane zero is the same as the regular zero. But instead of the phase going up, it'll go down. So here I reached the minus 20 dB per decade slope, but the phase now is 270 because instead of going up, it went down, so it's a difference of 180. So this is the meaning of non-minimum phase. In a regular system, without the right half plane zero, you have minimum phase. You have the phase of the slope dictated, while in the non-minimum phase system, you have an excess phase here, and this is actually the meaning of the non-minimum phase system. So let's move ahead now and talk about Nyquist criteria and the right half plane zero. Unfortunately, I think there is a lot of misconception about this point, so let me try to clear this up. Here we have a feedback system. We have the planned feedback. There's another gain block. The closed loop looks like this. This is the open loop, 1 plus beta A. This is the loop gain. Beta A is the loop gain. Now, the A closed loop, now expressed in the S domain, Laplace domain, will have a numerator and a denominator. These are polynomials in S. Also, this one is a polynomial in S. And you have solutions here. So you have zeros and poles. You have poles here of the A closed loop. However, this denominator by itself is also having a numerator and denominator. This is also a function, a certain function. So this denominator has zeros. The zeros of these denominators are the poles of the A closed loop. It's a little bit confusing, so let me go over it again. We have an A closed loop. There are some poles here. Now the poles here are actually the zeros of this expression. So if an A closed loop has poles in the right half plane 0, if this system has poles here, that's a no-no, it's an unstable system, it means that this denominator here has zeros in the right half plane. This denominator has 0 in the right half plane. So now we come to the Nyquist criteria. Let me start again. This is the closed loop response. Now it's expressed in the Laplace domain. Now I'm defining Z as the zeros of 1 plus LG, 1 plus the loop gain. Zeros of this thing. Zero of this thing are the poles of the A closed loop. And this is what we are looking after. We are looking for 0 for this thing. So Z is the poles of A closed loop. And then we have another term here, which is the poles. And these are the poles of the loop gain. This loop gain, again, has a numerator and denominator. And we are talking about the poles of this loop gain. And we are in particular talking about the right half plane poles of the loop gain. Right? Now what the Nyquist criteria is saying is the following. If you encircle the -1 point n times, okay, 0, 1, 2, whatever, then the number of zeros that you have for this, which is the number of poles for the A closed loop, the number of zeros, will be equal to the number of turns that you had here plus the number of poles of the loop gain. Okay? So let's take an example, make it clearer perhaps. Let's say that the loop gain looks like this, and purposely I've put here a right half plane 0. Now this is the loop gain. This is the loop gain. It has a 0 at the right half plane, but the poles are in the left side. Now normally the loop gain will not have poles in the right side of the complex plane, because the pole there means that this loop gain in open loop, this is actually the open loop, part is the system, part is the feedback, is unstable. Now we are talking about stable system. It could happen, but not in power electronics normally. Power electronics, the loop gain itself is stable. So there is no poles in the right side of the complex plane. So we don't have to worry about this. We don't have to worry about it. So the number of zeros of what? Of 1 plus Lg, which is the number of poles, is equal to the number of times you encircle the -1 point. So what's the contribution of the right half plane 0? None. Doesn't contribute anything. You don't have to take it into account. Obviously, it is changing the phase, as we've seen, so it could worsen the situation, but you don't need to take it into account here. Here is the poles of this thing in the right side of the complex plane, which normally we don't have it in a stable system by itself. In open loop, if the open loop is stable, we don't have this. This is 0. So just the number of encircling is the number of 0 of 1 plus Lg, which is the number of poles here. Okay, so we see that this really doesn't have to be taken into account in this thing. Well, it is contributing to the phase lag, that's no question about that, but it's a different story. So how can we simulate the frequency and time domain of a right half plane 0 in SPICE, say? Well, we can use an ABM, which is a analog behavioral model, and E Laplace is a nice block here, which you can write expression in the Laplace transform domain very nicely, and then you can run either a small signal or a large signal simulation. So I'm showing now a large signal simulation. This is a step of 1 volt fed here, and I'm looking at the output. I have a right half plane 0 here. I've also added a normal pole here. It's far away, it's 100 nano, the 1 over omega. And this is because I found that SPICE doesn't like to have just the right half plane 0 by itself. Somehow it's not happy with it. So if you add a pole, then everything works fine. So here it is. We have the input, which has a slope, a constant slope, and this is 1 volt jump, and the time here is 10 microseconds. So the slope here is 10 to the 5th volt per second. Now the output is the derivative of this. Being a right half plane 0, it's minus, and the value here is 10 to the 5th, because this is the slope. So everything works fine as we would expect. Now I've made an example which is more elaborate. This is now in feedback. There's a feedback loop here. Feedback loop is 1, and all the function is here, so I don't separate into a plant and a feedback. Everything is here, the feedback itself is 1. Now the expression here is more elaborate. First of all, I have a gain of 100,000. Then I have a right half plane 0 at actually 10 kilohertz. That's 10 kilohertz. And then I have a left hand pole, 10 kilohertz too. So what happens here is, as far as the slopes, these would cancel each other, because this is the plus 20 dB per decade, this is minus 20 dB per decade, but the phases would add, because this is minus 90 degree and this is also minus 90 degree. And then I have a low frequency pole, a regular pole at about 1 hertz, and that's this one, and then I have this one, which really doesn't matter much. So I have here now Two things. First of all, I can look at the loop gain. Here's the loop gain. So the loop gain will be defined as this voltage over this voltage. This is the gain of this loop here. And then I have also a time domain pulse. It's a current pulse of 1 amp. Well, this will accept anything. It's an ideal element. It's a 1 amp. And I can see whether the system will be stable, because a perturbation in the time domain is the best way to see if a system is stable or not. So I can do everything, and I also can look at a closed loop if I wish. I am not going to do it. This is 0 now. So let's see what we got. Here is the gain. We see here the amplitude. We see here it starts with high gain here. Then this first pole, so just below the 1 hertz. Then it goes down minus 20 dB per decade, and there is a minus 90-degree drop in the phase. There's a lag here of 90 degrees. And then we come to this point, which has both a right half plane 0 and a left side pole. So the slopes are canceling each other, so it's going on with the same rate, but the phase here drops 180 degrees because we have 90 for this and 90 for this. So this is now the phase of this particular case. Now let's have a look at the phase margin. Crossover here in this particular case is 0 dB, and it is the phase itself is minus 200, so we have a negative phase margin. This means that the system is unstable. This means that we are encircling the -1 point. Indeed, if I inject a step response, I see this starting to oscillate, and the oscillation actually goes up. I haven't run it long enough. So you can see that this system is unstable. What about the Nyquist now? Here we have the Nyquist. This is for the positive frequencies. This is the negative frequencies. This is here the -1 point, but we can't see it because the gain is very high here, so we don't see, and resolution is not good enough. So I'm going to zoom on it. Here it is. So this is now the Nyquist plot, and we can see that it's very nicely encircling the -1 point 1 time. So we have 1 pole in the right side of the complex plane. System is unstable, everything as it should be. What about the right half plane 0? Well, we don't care about it. Well, it's added phase here. This is why it became unstable, but we don't have to count it in this encircling of the -1 point. Now here's another example. I have now a phase margin of 40 degrees, so this is a stable system. And indeed, we can see here that in the time domain, we have sort of a little overshoot, will be consistent with the 40-degree phase margin. And then there is another example, and here I have the phase itself is 110, phase margin of 70, so this is a well-damped system. And indeed, this is the time domain. You see that you just see the drop. This is due to the output impedance of the amplifier. Let me have a look at here. Again, here, this amplifier put here 1 ohm. So when you inject a current here, there is a drop here at the beginning until the system stabilizes. So this is the initial drop here, and then it comes back. Now what about the Nyquist in this case? Okay, here we have the Nyquist. This is the positive frequency, negative frequency. Again, we don't see anything. So here is the zoomed picture. We see clearly that the Nyquist plot does not encircle the -1. It goes this way, and there is a little bit of a wiggle here. Obviously, the phase here is quite a bit over 180, but we don't care about it because it's not encircling the -1. And if I put here the unity circle, then of course this is the phase margin, which is consistent with what we have seen. So this is the picture, the frequency. So the system is stable, and the right half plane zero really doesn't play any role except for in this region, which is really not affecting stability anymore. Let me now turn to the issue of right half plane zero in PWM converters, which is the subject matter actually of this presentation. And I'm talking about CCM because we see this phenomenon in CCM operation mode. Now it turns out that we find the right half plane zero in the boost, buck boost, and flyback converters. The transfer functions here are 1 over d off, d on over d off minus, and then n times d on over d off. Notice that on all these, there is a dependency of d off. This turns out to be significant, as I'll show later on. It's sort of a hint what's really going on here. Still, when d on is going up, d off is going down, and v out to v in is going up. So the tendency of the output, the increase, is proportional or is dependent on d on. The larger the d on in all of these, the larger the d on, the larger will be the output. So let me try to explain the physics behind the right half plane zero in PWM converters. And I'm taking the example of the boost converter. It's the same for buck boost in flyback. So here we have a boost converter. This is the inductor, transistor, diode, and output section. This is the on time. I'm looking now at the black lines. This is the on time of this transistor. This is the inductor current. During the on time, the inductor current goes up. And then during the off time, it goes down because it is actually discharging into the output. At the same time, the output voltage during the on time is actually going down because during the on time, the capacitor is being discharged. The current of the inductor goes this way. Only during the off time, there is a current going to the output, which is discharging it. So now let's assume that there is a step in the duty cycle, so the pulse becomes longer. Obviously, the current of the inductor will get to a higher level. At the same time, the output will drop lower because we have now a longer on time. But then we are left with a shorter T off here, and this is where current is flowing to the output. Now the current is higher, so the rate here is higher, but still we will not reach the same value as we had before. Well, think even about, say, a duty cycle of 0.9, almost 1, there's nothing coming out, and the voltage is actually dropping, so that if you look now at the response of the system to a change in the duty cycle, this is sort of the average duty cycle, what you see is that the first time after you have the increase in duty cycle, the voltage is actually going down. Eventually it'll go up. This is the transfer function. D on is high, V out to V in is higher, but at the very beginning you do have this drop. This is the nature of the right half plane zero, that you start when you have a positive input, positive change, you have a negative response. Now obviously this is very bad for a feedback system, because if you like the output to go up and then you increase the duty cycle, as it should, and what you find that actually at the very beginning the voltage drops, then of course the system will react to this, and this really cause, in fact, it's a phase reversal, it becoming a positive feedback, and the system will oscillate. So this is why right half plane zero in PWM converters within the operating region are very bad. So let's have a look now on the implication here. Suppose we have a loop gain, and this is a regular loop gain. There's nothing special about it. All are zero and poles which are normal ones on the left side. So we have a pole here another pole, another 90 degrees, there is another one, then there's a double zero, so we go all the way here to 90 degrees. And of course, corresponding to this, we'll have a minus 20 dB per decade drop here. So this will be the crossover. We have a phase margin of 90 degrees. Everything is fine. Now suppose, this is one example, that instead of the regular zero, we are going to have a right half plane zero. Now, as far as the slopes go, it'll be the same, because the slope of a right half plane zero and the regular zero are the same. So therefore, here I'll find the same slope, because there's no change in slopes here. But the phase, instead of going up plus 90 degrees, going down. So therefore, you'll have a phase of minus 270, and obviously, this system is unstable. So you see that if you have here right half plane zero, that's trouble. Here's another example. Suppose one of the poles is replaced by a right half plane zero. In this case, the phase will be the same, because the phase of a right half plane zero is the same as the phase of a regular pole, but there's a difference in the slopes. So in fact, rather than the slope here going down, it'll go up. So eventually, you'll reach here a slope like this. This is very bad, because the next crossing will definitely have a large phase shift, and the system will be unstable. So therefore, right half plane zero within the loop gain is very bad. So what normally is done is to shape the loop gain in such a way that the crossover will be lower than the right half plane, the location of the right half plane zero, by say at least 30–50% in terms of frequencies. So if you have an open loop response like this with the controller, you'll shape it so that the crossover will be here, and you have a safe distance here, and everything will be fine. This is not so bad today, because the switching frequency of modern switch mode systems is much higher than it used to be. Say for 100 kilohertz or 60 kilohertz switching frequency, this would be, say, the open loop gain. But with 300, 400, or maybe 500 kilohertz switching frequency, we'll have a much wider range of the open loop gain, and therefore if you chop some of it, well, it's not so bad, because you are left with quite a bit of a bandwidth in the closed loop, which is not so bad. What else can be done in order to eliminate the right half plane zero? Well, one way is to use DCM. The right half plane zero is pronounced in the CCM, continuous current mode, as we have seen before. In DCM, it can be eliminated as a matter of fact. So let's have a look what's really happening in the DCM, and I'm again referring to the boost converter. Again, we look first at the black lines. So here's the inductor current going up, going down, up to zero, then there is a rest time, and then it's going up again. Now the output at that time, here it's going down because there's no current at the output, but here it's going up. This is the time that the output capacitor is charging. Now if I increase the duty cycle, obviously the current of the inductor will go to a higher level, and then it'll drop. This is the time now that the output will charge. Now we have a much higher current, and consequently we're going to have a fairly large jump, so that we'll have a higher voltage after this change. So we have eliminated, or we don't see, the drop, which is the reason for the right half plane zero. So by operating it in DCM, we can actually eliminate the problem. Obviously, DCM has its own problems of high RMS, but this is not the issue here. Another way, which is a little bit more complex, and let me just go over it, is to first of all use leading edge modulation. I'll talk about it in a minute. And then to rely on the ESR, you need a fairly high ESR in this case. So let's see what's happening in this case. First of all, let me define what is a leading edge modulation. Leading edge modulation. In a trailing edge modulation, which is the normal way PWM modulation is being done, we have a switching period, we have the pulse, and then when the duty cycle is increased, the on time is increased, we are increasing it this way. So this is the trailing edge of the pulse. There is another way of doing it, and that is if this now is defined as the period, and this is the on time, we change the duty cycle this way. The on time is changed this way. So this is now the leading edge of this pulse. So this is the leading edge modulation. Now, another issue here that needs to be clarified is the fact that if you take ESR into account, the shape of the voltage at the output, the ripple, will have jumps here. Well, the reason for the jump is that when the current is flowing and charging the capacitor, you have a voltage on the ESR, so that the V out is higher than the capacitor voltage. During this charge, when the transistor is on, the current going this way, you have a negative voltage, so the voltage is lower than capacitor voltage. So each time you switch from charging to discharging of the capacitor, you see these jumps. Okay? So let's assume that we are running the system in a leading edge modulation. And now we have increased the on time, increased the duty cycle. What will happen is, of course, that we'll start charging faster or sooner, and we'll go to a much higher value of the current because now we have longer time. At the output, we're going to see here a drop, and this is the drop, this is the discharge during the on time. Now the output is discharging, but since here we have a much higher current, the drop of the ESR will be larger so that we can get a higher voltage. So after the change, we're going to have a higher voltage at the output, which means that we have sort of eliminated the right half plane zero. Now obviously the ESR has to be large enough, so there are some conditions depending on the values of the other components that will dictate what is the value of the ESR in order to have this voltage higher than this one. So you need a higher ESR. Of course, there are higher losses because of the current flowing through the capacitor, but this can be done, and actually it's been shown by Dr. Ray Ridley many years ago with some other co-workers. Now, how can we build a leading edge modulator? Let me start with the trailing edge modulator, PWM modulator. Here we have an output, we have a divider, we have the error amplifier, it's a minus sign. Here, the inverting. This is a comparator, and we feed a triangular waveform to this comparator. Now this broken line here is the level here, so as it hits here, the triangular waveform, we get an on time, which is this time here. Now suppose the voltage of the output will go down, here it will go up, and this level goes up, this level here goes up, and consequently this time will be longer. So this is a modulator, a regular trailing edge modulator. Now in the leading edge modulator, we have here everything is the same. So the divider, have the error amplifier, but notice that now the triangular wave is sort of inverted. We start with a high level and then we go down. So here again, if we are at the steady state, this is the broken line, the black line here, this is the level here, then we'll have this on time, because here it starts with 0, and then we have here the on time. Now if the voltage drops, this goes high, and this goes high, and therefore we'll move backward, sort of, and this T-on will be longer, so we have now this leading edge modulation. So it's very simple actually to build a leading edge modulator. It's really the same thing, it's just a different waveform that we have for the triangular wave. And there are of course many other ways to handle the right half plane zero and PWM converters. Well, most of them are actually rely on nonlinear control. I'm not going into it, and there are many digital ways to do it, digital control method. Let me just say that none of them is really a knockout. That is, none of this, the method is really solving the problem in all cases. So you can handle it in one way or another, but the conventional way of just shaping the controller such that the crossover will be at a lower frequency than the right half plane zero is probably the most safe to go. So this actually brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting and perhaps it will be useful to you in the future. Thank you very much.